Okay, let's begin again. So, as we were talking about that problem from last class, let's see, there was the LT spice simulation. In the LT spice simulation, we can see how a DC voltage of 5 volts and an AC voltage of a square wave of 10 volts peak to peak can be combined using this kind of resistive network to obtain an output that goes from 0 to 5 volts. Effectively, what we are doing is we are chopping off the negative cycle and we are shifting the waveform up. Okay. And so let's look at the theoretical analysis for this circuit. So the circuit looks like this when it's transformed, not transformed, sorry, just redrawn. You got voltage source V1 on the left, that is DC voltage. V2 is that AC input voltage on the right. And V out is measured between the two resistances. And let's look at just the positive cycle, right? If you look at just the positive cycle, what do we see? I'm going to copy this and paste it here. Okay. The one in green is our DC voltage, V1. This is V2. Okay. And analyze just for this first time period, positive half cycle, meaning only this portion right here. Okay. When we analyze just for that portion, what do we have? We have these two resistors. They are of equal value. We have plus 5 volts DC on the left, and we have plus 5 volts DC on the right. Sorry, not plus 5 volts DC, but plus 5 volts on the right. Again, this is just for that first half cycle. Okay. Right. So it's plus 5 volts here for DC. It's also plus 5 volts here, just for that first cycle. Everybody with me so far? Okay, here's the important question. If both ends of that branch is at 5 volts, what is the voltage, the effective voltage between those 2 points? So that plus 5 volts is with respect to the ground point right here. This is V out. Let's call this loop 1. This is loop 2. Okay. So that point on the left is at plus 5 volts. The point on the right is also at plus 5 volts. Then what is the difference between the 2 points? Zero. There is no difference because they are the same. The key point is the difference. If both are at 5 volts, there's no difference. Same thing. Voltage is the potential difference. If there is difference, if there is no difference, that means the voltage is zero. If the voltage at both ends of those resistors is zero, what is the current? Also zero, which means the voltage drop across these resistors is 0 volts. If the voltage drop across these is 0, you apply KVL, what do you obtain? You can apply KVL to loop 1. What do you all think? So let me just write it out. Here, loop 1 KVL. What do I have? I have 3 voltages in loop 1. I have my voltage source V1. I have the 0 volts from the resistor. And I have V out. They should all equal 0 volts. So V1 minus plus 0 plus V out gives me 0 volts. Therefore, V out is equal to V1 is equal to 5 volts. That's mathematical proof that my V out is at plus 5 volts. Okay, V out is at plus 5 volts. So look at that LT Spice simulation. It keeps disappearing, but you see here, for that first half cycle, V out is plus 5 volts. Everybody see that? Right? Let's go back to here. And I can prove this by applying KVL to loop 2. KVL is law. It's a law of physics, inviolable, based on conservation of energy. And so we apply KVL in the left loop, and we obtain V out as 5 volts. We apply KVL in the right loop, we must obtain V out as 5 volts. That cannot change. So let's apply it. If I sum up on the left side, I have, sorry, so I sum up on the right side, I have V out, I have 0 volts, and I have V2. If I sum it all up, I should equal 0. Minus, plus, and plus. And I get V out is equal to V2, which is 5 volts. So that confirms my answer. By applying KVL on the left side and apply KVL on the right side, I obtain 5 volts. That's mathematical proof right there. Okay, that's the analysis. Does everyone see that? What happens in the negative half cycle? In the negative half cycle, V1 is still at 5 volts, but V2 is now at minus 5. Okay, so in the negative half cycle, this is what's going to happen. This end is at plus 5 volts. The right end is at minus 5. If the right end is at minus 5, and of course V out is here. This is basically here. What is the difference between the two endpoints now? $10, right? Plus 5 and minus 5, so 10 volts. So now we will have current flowing through those resistors. But here's the thing. Because both resistors are equal in value, 10K does not matter. The value of the resistors does not matter. Okay. The value of the resistors does not matter because we are not talking about the value of the current. Talking about voltage. Because both resistors are of the exact same value, that means that 10 volts is divided into exactly half. So half is on the left, half is on the right. But in this case, it's plus 5 on the left, minus 5 on the right. What is halfway point between those two voltages? 0. That's your answer. So V out is 0 volts. So negative half cycle, when this is the case, your V out goes to 0, which is right here. Purple V in, sorry, not purple, this blue this kind of like dark blue or whatever, node 3, the second waveform, it's minus 5 volts, right? It's minus 5 volts. So negative half cycle, V out is 0 volts right there. So simulation proves the same thing. Theoretical manual calculation and analysis also proves the same thing. And V out is to 0. And hence, as a result, we obtain a waveform that is shifted up. It's shifted up by about 2.5 volts. You apply 5 volts DC, and it shifts up by 2.5. Right? Your original waveform was centered at 0 volts. Now it's centered at 2.5 volts. Let's take a pause. Let me know if you have any questions. Yes. Effectively speaking, yes, we chopped out the negative half. Effectively. Yeah. You could say that is a downside of using resistors, because resistors will consume voltage, it will consume energy and dissipate it as heat. So we can say, yeah, effectively that one is lost. Yeah. Yes. Sure. Yes, that is correct. So it's related to the same point that was brought up earlier. So the question being asked is, would we expect this kind of circuit to go, instead of going from -5 to +5 and shifting it from 0 to 10, is it because of the resistors? The answer is yes, because of the resistors. There are diode clamper circuits that are made from diodes and capacitors, and those will actually will truly simply shift the level up. But capacitors is something we will see in 215, or you will see in 215, 215 next quarter. Now, capacitors are energy storage devices. So unlike resistors, they will receive the energy, and then they will add it to the energy in the negative half cycle. And so the voltage at the output is a combination of the negative input plus the stored energy in the capacitor. And so V out is now. And so there you can get 0 to 10 volts. But that's a discussion for next quarter. Okay. But diodes are a way of doing that. And we are learning diodes in this class. So we can have clamper circuits using diode. But yes, in this case, it's chopped off or it's less. It's because of resistors. So resistors will consume a portion of that energy. But now let me ask you a question. Looking back at the circuit diagram, how can you change the circuit so that instead of going from 0 to 5, we go from 0 to -5? So V out is going from 0 to +5 volts. If you wanted it to go from 0 to -5 volts, what would you change? No, not quite. Absolutely. You flip the DC voltage source. So if, instead of applying +5 volts, we are now applying -5 volts. Okay. And so I can flip the voltage source here, but an easier way to do that is simply change the numerical value. Change it to -5 and keep an eye on the purple waveform, specifically the numbers on the y-axis. Okay, right at the bottom, right here. So I'm going to run. And this is the advantage of simulations. Simulation software. I'm just going to run and keep an eye on this right here. Oh. You see that? It goes from 0 to -5. Now shift it -2.5. Okay, we're simply clamping it negatively. If I apply a 10-volt source, if I change, so we went from +5 to -5. Now I'm going to +10. Where do you think the center of my output would be? 5. So if I do this, center is at 5, waveform goes from 2.5 to 7.5. If I change that 10 to 100, output is centered at 50. So we applied 5 volts. It was centered at 2.5. You apply 10 volts, centered at 5. If you apply 20, it will be centered at 10. If you apply 100, it will be centered at 50. Yeah. Yes. It's shifting it. Yes, exactly. And this would be a good way to develop a better understanding. So for each one of these simulations we did, it's a calculator. So we don't have to think, just you press a button, it just calculates automatically, right? But perform the theoretical analysis and verify yourselves that you obtain it that way or not. So we just did the 2 KVL equations for both positive as negative half cycle right here, right? You have these. You have the KVL expression here, and you have expression here, right? So you apply these KVL expression for both positive cycle as well as the negative cycle, and you can simulate this for a variety of voltages. All you have to do is change V1, right? The equation is already there. All you got to do is change the value for V1. And you can calculate the output. You can also calculate the current, right? And so to broaden your understanding or have a more in-depth understanding, you can run the simulation. You can also perform theoretical analysis yourselves. Okay. This is something that will come up on the quiz on Monday. Some variation of this. Okay. All right. We have 15 minutes. So let's move on. Talk a little bit about current and voltage division. Okay. So we covered the current division and conductances. And so just want to do a summary that in a parallel connection of resistors, no matter how many resistors you connect in parallel, voltage is the same for all resistors. However, current is divided. And because current is divided, we can develop and apply an expression that is known as current division principle. So for example, we have a random collection of resistors all in parallel, like n resistors in parallel, and we want to find the current that is flowing in each one of those resistors. We can apply current division principle, and we can calculate the current by simply using conductances of these of these resistances. So we have, if you're talking about I1, then we want G1 all the way up to Gn times your source current Is. Okay, the G1 over G1 plus G2 all the way up to Gn. And then if you have a series connection of resistors, then the current is the same. And voltage is divided. Let's say again, you have n number of resistors all connected in series. You're trying to find the voltage across each one of these resistors. And that is given by the voltage division principle. R1 plus R2 plus R3 all the way up to Rn times the total voltage that is being applied, or the source voltage. Okay. This is true no matter how many resistors you have connected in parallel or in series. So these principles, voltage division principle and current division principle, will remain true no matter how many resistors you have. You have 1, 2, 3, 4, 5 resistors in parallel, or 1,000,000 resistors in parallel. That principle applies. Same thing for voltage division. And the reason it applies is because voltage division and current division are both shortcuts. And they're shortcuts that are derived from Ohm's law. We already saw the derivation in some of the previous slides, right? So they're simply shortcuts, but they're both derived from Ohm's law. Okay. All right. So this, again, is something I will assess on the quiz on Monday. So expect a question about voltage and current division. Okay. Guaranteed. All right. Then how many of you installed LT-Spice on your devices? Okay. It's a very powerful software. It's based on a, I don't know if I ever mentioned this in class, Origins of Spice. All right. Okay. Sometimes I forget because I'm teaching so many things. I don't know if I brought it up or not. So it's based on a technique called nodal equations or nodal analysis, and or to use its full form, node voltage analysis. And that's a technique that we'll look at in week 10, last week of classes, at the very end. Okay, so nodal analysis and mesh current analysis, those two techniques are again circuit analysis techniques that we'll look at almost at the very end. From now until then, we'll look at diodes, applications of diodes, applications of resistors, op amps, and comparator circuits. So in circuit analysis, if you're just learning, then you're simply learning the devices, and we're just learning about, the theory of those devices. But in EE 115, it's a fantastic course, as or at least my view is that it's a really great course, because we are not only looking at these components, we're actually looking at how we can apply, or the applications for these components. So one of the applications we saw was voltage division. We can try and obtain different source voltages from a single source, right? In the previous couple of slides, we had a source of 9 volts, but we are deriving a 5-volt source from it. That's an application of resistive networks. Okay, this was the home activity that was assigned, right? So again, if you have not done this, go ahead and do so. The solution is here. That's for solving with superposition. And you can also solve it manually. These questions are more for students to think about, because again, I will test something similar to these questions on the quiz. Okay, what will happen if the resistor spots are interchanged? What will happen if the voltage or the current sources are flipped? Intuitively, what do you think would happen? I may ask this as a short answer question. I may ask this as a problem itself. Okay, just something to think about, right? I'll give you the answer to this one. If you have a voltage source like this and you flip the current source so that both of them are going up, voltage source has plus on the top, minus on the bottom. So current always goes from minus to plus, so it's going up. Current source goes up. This bends here. This is coming through here. And KCL, if you apply KCL, it's there, right? So both of them are coming up, they join up, and so they are summed up. And so the current will actually increase because of the voltage source and the current source both acting in the same direction. So the answer to question number 2 is that if the current source was flipped, then the output current I would increase in value because both currents are coming in the same direction. So now there's more of it to go in the last branch. So the question being asked is, would it be that there is more current flowing in the 5 ohm versus the 2 and 3 ohms? I don't think so, no. So if it's on the left, let's see. No, because current in the 5 ohm resistor is coming not solely, but it's coming from the power supply. It's going from left to right. Do you see that? This is the 5 ohm resistor, this one, right? If you apply KCL at the top here, what do you see? I is a result of the current that's flowing from the current source as well as the one in the 5 ohm. So by its very definition, by its very nature, I must be larger than that 5 ohm current because the current source is adding on to it. Not in the 5 ohms, in the 2 ohm. Yes, I thought you asked the other way around. Okay, yeah. So the question being asked is, would there be more current flowing in the 2 or 3 ohm resistor than in the 5 ohm resistor? The answer is yes. And we can easily prove that by KCL. Okay. All right, 5 minutes left. Let's go to next one, which is a little bit of signal processing of resistors in okay. So as I stated just a few minutes ago, we're going to look at a few more applications of resistors and then biasing applications of resistors and then a few other things. So let's talk about bias. What is bias? Anyone know what bias is? Okay, bias is basically the external constraint we place on our electrical system so that it functions only in a certain range. Okay, in simple terms, biasing simply means we are applying a specific voltage or we are applying a specific current to our circuit so that it functions and gives us a specific output. That's what is known as a bias. So in the lab, you have already used diodes. You may have come across the term forward bias and reverse bias, perhaps. Diode has 2 terminals, anode and cathode. Anode is positive, cathode is negative. If the anode is applied the positive and cathode is applied the negative, meaning plus and plus, and the anode is at higher voltage than the cathode, and we say the diode is forward bias. And if we reverse that, meaning the cathode is higher than the anode, then we say it's reverse bias. Diode is not a linear device. It is a non-linear device. The voltage and current do not have a linear relationship. And it only functions in one direction. It's a one-way device. It only functions in forward bias, meaning when the anode is positive and the cathode is negative. So when we apply a bias to a diode, we have a specific purpose. We want it to operate in a forward bias mode. Then we apply voltage in a specific manner, and that is known as biasing. Okay. Resistors dissipate energy or electrical energy as thermal energy, as heat. Okay. It is an unfortunate byproduct of energy conversion. Electrical energy is converted into thermal energy. We use this property in electrical circuits and electronic circuits. It is highly undesirable, but it's an unfortunate byproduct of everything. So we have our circuits, they all heat up. You know, cell phones, laptops, desktops, we have circuits in there. We have massive heat sinks to take away all the heat. We have fans and cooling systems in there. It's an unfortunate byproduct. However, we also use these applications in everyday life. So if you think about electric coils inside your, let's say, air fryer, cooking stoves, say electric griddle, clothes iron, space heaters, hair dryers, all of those use this property. It's simple. You have a piece of material and you pass electric current to that piece of material. It opposes the flow of current, and that opposition results in the conversion of electrical energy into thermal energy, meaning heat. And you can use it to cook. You can use it to iron your clothes. You can use it to dry your hair. You can use it to heat up your space heaters. And so that's a place where we actually use, you know, the resistive portion and the byproduct of heat. Okay. So those are the places where it is actually desirable. When we turn the dial on these devices, on these appliances, what we are doing is we are changing the amount of voltage or the amount of current that is being applied. So we are changing the bias. On the outside, it would say, okay, you want to set the oven to 200 degrees Fahrenheit. But what is happening inside is that you're changing the voltage and the current. So you're forcing that heater element to function within a certain range so that the heat that is generated will not cross 200 degrees Fahrenheit. So you're biasing the device, electrically speaking, to function at that specific range. So when you change the dial on the oven or on the cook stove, you're biasing it to generate only so much heat. So you're constraining your system to function within that range. And in those applications, the heat is desirable. Okay, the heat is desirable. But for the most part, in electric and electronic circuits, it's not desirable. All right. All right, so we'll end class here today, and we'll pick up here on Monday. Monday, there's a quiz based on everything we've done this week. So voltage division, current division for sure, maybe short answer to questions based on concepts, and then the clamper network that we just saw, that we spoke about in LT Spice. Okay. All right. Have a good weekend, and I'll see you all on Monday. Sure.